Okay, so there are a total of 6 properties that we would like our algebraic structures to have. And the first quarter of the course is spent examining all 6 of these properties. We start with the property known as the commutative property, which is one that you are probably familiar with from your high school algebra courses. We start with a definition. Now, since this is our first definition of the course, I will say a word about definitions. It is very important in abstract algebra that you memorize your definitions on the day you learn them. You will get 3 or 4 definitions every class, so that will be well over 100 definitions over the course of the semester. You need to learn them the day that you get them, otherwise they will build up on you. And you will find that you won't be able to write proofs if you don't know what the definitions are that are involved in the proofs. So whatever works for you to learn definitions, whether it's write them out or put them on flashcards or say them to your roommate either in person or on Zoom or teach your parents or whatever, do what you need to do to learn the definitions. Okay, so for the definition of the commutative property, we're going to suppose that both S is a set and star is an operation. Now, the way that we define this is we say that star is commutative on S. In other words, operations are commutative on sets. So star is commutative on S. And hold on, we'll see if we have the star in the symbols here. Okay, so star is commutative on S means for every pair of elements A and B in S, every pair of elements in the set, A star B equals B star A. Now, in other words, this is saying, the commutative property is saying, given 2 elements, you can combine them in either order. Now, I want you to go back and look at the 4 familiar operations, addition, subtraction, multiplication, and division, and think about which 2 of them are commutative. Pause the video for a second and think about it. It turns out that both addition and multiplication are commutative operations. And these are facts that we accept as axioms. So these are our commutative axioms. Now remember from foundations, an axiom is something that is obviously true and that we accept it as true without proof, because proving it would be impossible just from the definitions that we have. And the 2 commutative axioms that we accept are that addition is commutative on the set of real numbers. And what this means is that for every pair of elements, A, B, in the real numbers, A plus B equals B plus A. And multiplication is commutative on the set of real numbers. And this means that for every A, B in the set of real numbers, A times B equals B times A. Now, let's see. These are things that we accept as axioms. We accept them as true without proof. You would have seen A plus B equals B plus A and A times B equals B plus A without this carry quantifier in the first chapter of your high school algebra textbooks. Now, these are things that we just accept to be true. For example, we know that 2 plus 3 would equal 3 plus 2. Both are equal to 5. And what the commutative property of addition tells us is you can either add the 2 on the left and the 3 on the right, or the 3 on the left and the 2 on the right, and you're going to get the same thing. Now, for multiplication, this would be saying that an illustration of the commutative property would be 2 times 3 equals 3 times 2. Both are equal to 6. Now, let's just be very careful though. These examples illustrate the commutative property, but they do not prove the commutative property. And the reason why is the commutative property is for every pair of elements A and B in S. And here we have just illustrated this true for one particular pair of elements AB, for the element A equals 2 and B equals 3. Now, showing something is true in one instance does not imply that it is always true. So you cannot prove a statement with a for all quantifier simply by giving an example. Just because it's true for one pair doesn't mean it's true for every pair. This is a very important theme that we'll see in this course. When you have a for all statement, you cannot prove it just by giving a single example. And in fact, because there are infinitely many real numbers, and thus infinitely many pairs of real numbers, you cannot prove this commutative property on the reals simply by checking every single possible pair, because there are infinitely many pairs. That is why we accept as axioms without proof that addition and multiplication are commutative on the set of reals. The last comment that I would like to make about the commutative property for addition and multiplication is that commutative is a property of an operation. And what that means is addition is a commutative operation. Once we know that addition is commutative on the set of all the reals, we know automatically that it is commutative on any subset of the reals. For example, if I wanted to show that addition was commutative on the integers, if I took any two integers A and B, well, if A and B are integers, because Z is a subset of R, A and B are reals. And because we know addition is commutative on the reals, A plus B equals B plus A. Thus, addition must also be commutative on the integers. And that same argument for it would work for any 12 of these subsets here. Now, addition and multiplication are both commutative. And commutative is a property of those operations, meaning that once we know the operation is commutative on the large set R, it's automatically commutative on any subset of R. Okay, more to come shortly.